All right, let's be honest. If you're prepping for the meet, you know this feeling all too well. You totally get the physics concept, but then bam, the calculus in the problem just grinds everything to a halt. It's like hitting a brick wall, right? You understand the physics, but the math, that's what's costing you precious time and, let's face it, points. You see a question asking for instantaneous velocity or work done by a variable force, and it's so easy to just get bogged down in the numbers. Well, today, that all changes. So, let's just completely reframe this. Calculus is not some academic hurdle. Think of it as a high-performance toolkit, custom-built to solve these exact kinds of physics problems. We're not going to do abstract math today. We're going to add 3 super powerful tools to your problem-solving arsenal. Okay, let's open up that toolbox. Tool number 1, we're going to call it the instantaneous rate detector. Now, you probably know it as differentiation, but its real job is way simpler. It tells you exactly what's happening at one single specific moment in time. So from now on, whenever you see dy dx, I want your brain to just immediately think, how fast is y changing right now? Not the average change over a minute, but the precise, razor-sharp rate of change at this very instant. That's the whole magic of it. And every good tool has a user manual, right? Well, these are the core functions you absolutely have to know. The power rule, that's your bread and butter. You're going to use it all the time. And if you see anything about waves or oscillations, you'll need those sine and cosine rules ready to go. And here's the best way to think about it in the real world. Your car's speedometer, it doesn't show your average speed for the whole trip, does it? Nope. It shows your speed right now. That's the rate detector in action. Same thing for acceleration. It's just the instantaneous rate of change of your velocity. So here it is, the big takeaway. When a physics problem gives you an equation for displacement and asks for velocity, you know exactly which tool to grab from the toolkit. You pull out your rate detector, you differentiate, and you are already halfway to the answer. It's that direct. All right, let's put this tool to the test. We've got displacement, and we need the velocity right at t equals 2 seconds. First things first, we use our rate detector to differentiate the equation. T cubed becomes 3t squared, and that negative 2t just becomes negative 2. Easy enough. Now we just plug in our time, t equals 2, run the quick math, and we're there. And boom, just like that, we have our answer. 10 meters per second. See how powerful that is? It's clean, it's precise, and most importantly, it's fast. Okay, on to tool number 2. Let's call this one the grand total accumulator. You know it as integration. And get this, it's the perfect opposite of our first tool. If the rate detector breaks things down into single moments, the total accumulator, well, it sums them all back up. The key idea here is all about adding up something that's constantly changing. You know, imagine a rocket that's always accelerating. How do you find the total distance it's traveled? You can't just multiply speed by time because the speed is always changing. You have to use the total accumulator, integration, to sum up all those teeny tiny changes in distance. And visually, it's simply the area under the graph. Now here's a neat trick. Look closely. These formulas are the exact reverse of differentiation, aren't they? With the power rule, you do the opposite. You increase the power by 1 and then divide by the new power. Sine and cosine are just flipped. It's a perfect mirror image of what we just learned. This slide right here, this is the whole game. It shows you the entire picture. Differentiation is like walking down the ladder, from displacement to velocity, then down to acceleration. Integration, that's how you climb right back up the ladder, from acceleration to velocity and back up to displacement. They are literally 2 sides of the exact same coin. Okay, our final tool is a special one. This is the Peak Performance Optimizer. This is the pro tool you pull out when a question asks for the maximum or minimum of something. The highest a projectile can go, the fastest possible speed, the greatest range. This tool finds the absolute best case scenario. So here's the basic idea, and it's actually pretty clever. At the very, very top of a curve, at its peak, the slope is perfectly flat, right? It's 0. So what we do is we use our rate detector to find the slope. We set that slope equal to 0, and then we solve. That tells us exactly where the peak is. But let's be real for a second. In a timed exam, who has time for all those steps? The standard method works, for sure, but it can be slow. So let's add some serious upgrades to our peak optimizer. We're talking powerful shortcuts that are going to save you a ton of time. These right here, These are your exam day secret weapons. You see an expression with sine and cosine? Bam, you can get the max value instantly with that first formula. A quadratic equation? There's a shortcut for that too. And my personal favorite, if you need to maximize the product of two numbers that add up to a constant, just make the two numbers equal. These shortcuts can turn a 5-minute problem into a 10-second solution. Seriously.
Okay, your toolkit is now complete. You've got the instantaneous rate detector, the grand total accumulator, and the peak performance optimizer. Let's do a super quick, rapid-fire recap to lock it all in.
Tool 1, the rate detector. What's its job? Finding the instantaneous rate of change. Just think, V equals ds over dt.
Tool 2, the total accumulator. Its job, finding the total sum or the area under a curve. A classic example, work equals the integral of force dx.
And for our peak optimizer, you gotta remember that killer shortcut. To get the maximum product when the sum is constant, just make the parts equal. It is a simple trick that's a huge time saver.
So there you have it. That's your complete calculus toolkit for physics. You know what each tool is for, and you know exactly when to use it. The key now is to put them to work. Stop seeing these as scary math problems and start seeing them for what they are, physics challenges that you now have the perfect tools to solve.
So the only question left is, which physics problem are you going to go out and conquer first with your new toolkit? Go get 'em.